Today we are going to talk about the junction properties, chapter 2. And first, we are going to think about the surface. Surface is different from the bulk. So we may think that we have a kind of junctions, different energy states there. Normally, what we can see is that if it is a semiconductor, then we're going to have a conduction band and the valence band, something like this. And then in equilibrium, the Fermi energy is the same everywhere, right? But when we have a surface state, if we fix the conduction band and the valence band, then this Fermi energy should be go down far away from the conduction band because of the surface states. Okay? So at equilibrium, we have to draw this to make the Fermi energies flat, same everywhere for equilibrium. That is the definition of the equilibrium. So we have to bend the conduction band something like this, and the valence band. So there is some field from the surface to the bulk because of this band bending. See, if you make a derivative of this energy potentials round EC over round X this should be related to the electric field which exists in the material. So if you have a crystal and at the surface is different from the bulk, the energy states is different. For example, if you talk about the silicon, for example, you know, the silicon has a covalent bonding, something like this, right? And at the surface, you are going to have a dangling bonds because there's no bonding at the surface. So one bond is missing actually at the surface, and this dangling bonding takes some charges from the air. We call it contamination, whatever, you know, the adhesion of oxygen in air, something like that, so that this surface state should be different from the bulk. So we can regard this as a junction. Now, if you talk about the bulk materials, the big, thick materials, this surface state or surface junction, if you like, is not a serious matter. But in a semiconductor business, we are going to talk about the thin films, which the thickness is less than 1 micron. Then the surface state talks. Okay, the surface state becomes very important. Now the next topic is going to be metal junction. Metal junction is not important because we cannot measure this. If you have a metal and metal AB with the different work functions, okay? In other words, it has a different Fermi energy levels. But if you make junctions like this, the Fermi energy should be equal everywhere so that there is a net electron flow between A and B to set up some field. But physically speaking, in the metals, there are so many free electrons. This internal field is not that serious. Besides, we cannot measure that because if you use a C metals to measure the difference between work function A and B, then as has been written on the text, what we can see the potential is phi A. That is the work function difference between the electrical lead C and A. And we are going to have work function difference between two materials that we want to measure. And then that different potential has to be measured through the lead C so that the total we can get, the potential, is going to be 0. So we cannot measure the work function difference between the metals. There is a way, however, to measure the work functions. For example, if you put the metal A here and metal B, you make a separate those two metals, and then you use the electron beam, and then you see the reflections. Okay, and then you just measure the angle here, and then you can convert this to the work function difference between metal A and B. So there is a way to measure the work function difference, but the junction itself is not that important in terms of the electrical properties. Okay, and we can talk seriously about the junctions from the metal and semiconductor junctions. The next topic is metal and semiconductor junctions. There are two kinds of contacts in this case, two kinds of contacts is possible. One is the ohmic contact, the other is rectifying contact. Okay, this rectifying contact sometimes called the blocking contact, okay, or Schottky contact sometimes. For example, N-type semiconductor, if there is a contact between N-type and the metal, if the metal work function is greater than the semiconductor work function, then it's going to be blocking contact. But if metal work function is less than the semiconductor work function, then it's ohmic. And the reason is that in the metal there is a lot of electrons all the time compared to the semiconductors. So if you make junctions between metal and semiconductor, always the electron is supposed to flow from metal to the semiconductor. But if you have work function of a metal is greater than the work function of a semiconductor, then the electron has to flow from the semiconductor to metal. Then there should be a barrier for that. And that barrier can be drawn. This is a vacuum level, for example, and then this is the Fermi energy of metals. Then it means that in metal system, the electron is just filled up to the Fermi energies, so that the definition of Fermi energy in the metal is the energies which the most energetic electrons can have. That is the definition of Fermi energies in a metal, right? But in a semiconductor, you're going to have, if you make a junction and make it the equilibrium, then the Fermi energy should be same across these junctions, so that the band has to be band like this, if it is the N-type. If you make a junction to N-type semiconductor to this, then the band bending in this much is going to be called chi-s, and this is the energy barrier. Okay, and then this band bending of conduction band is corresponding to the work function difference between metal and the semiconductors. Okay, that is the band structures when you form a contact between metal and the semiconductor, especially for the case that the work function of metal is less than the work function of the semiconductors. Okay, here the chi is affinity, electron affinity. Now, phi ms is the work function difference between metal and semiconductor. Okay. And here the phi b is a barrier height, and that is phi m minus chi s. This is not a work function of a semiconductor, the affinity of semiconductor. Affinity means the electrons in the conduction band in a semiconductor, the energy of electrons in the conduction band and the vacuum level, and energy in the vacuum level, the difference. We call that affinity. The energy required to take out the electrons from the semiconductor, okay? And the semiconductor case, the most energetic electrons is in the conduction band, not in the Fermi energies, Fermi levels like metals. That's the difference between metal and the semiconductor, right? Now here the important thing is the built-in potential. Built-in potential. And this built-in potential is the phi b, the barrier height, minus EC minus EF, the activation energy. We call this the activation energies in terms of the Boltzmann statistics, right? This is activation energies. Now, in the Boltzmann statistics, the electrons in a conduction band can be set effective density of a conduction band, that is going to be n sub c, right? Et minus E star over kT, and here the E star is the activation energy, which is corresponding to the energy difference between the conduction band and the Fermi energies, right? And here the Fermi energy is electrochemical potential. Electrochemical potential of the semiconductors. Now, the barrier height is related to the energy difference between this, like this, and then when you take out, subtract the activation energy for this, then that is going to be called built-in potential, and this built-in potential is actually the potential exists in the junctions, inside the junctions. And that is going to be equal to the round EC over round X. This X is the physical distance. Okay, so actually this is the slope of the conduction band along the x-axis. Let me see. This is the field. So actually, this is not equal to this. Let's say this is a built-in electric field. So that is actually coming from the around phi over around x. The electric field should come from the potential derivative of potentials, right? So you can see when you make a junctions between metal and semiconductor, then the band bending is going to look like this. And this is the Fermi energies, and this is the conduction band. Okay? And we can draw the charge densities according to this. Let's say if you distinguish the bending area, then you see we are going to have charges, and in the metal you are going to have a very shallow, like a delta functions, charges right at the surface of the metals. Okay? And accordingly, you can draw the electric field in this case, and that is going to be the most of the electric field exists in the semiconductor, but none of them is going to be here in metals. Okay, that is the X. And we can draw the potential corresponding to this. And most of the potential variation happens in the depletion region of the semiconductors. Well, the charges is nothing but the volume XdA. This is the volume, okay? Volume of depleted region. So if you say this distance is XD, and an area of the junctions is A, that is area of the junction, then the charges existing corresponding to this shaded area should be written like this. And if you say the charges here is Q prime, Q should be equal to Q prime all the time. Otherwise, charge neutrality cannot be maintained. Charge neutrality. So you can calculate actually the charges which should be in the semiconductor part of this metal semiconductor junctions, and that is composed of ionized donors. Okay. So if it is the N-type, then when the donor is ionized, then you give out the one electrons, and then itself is going to be ionized as a positively ionized charged to give one electron out. So at this junctions, which means that the electron is going to be deprived, moved to the metal, so that in this depletion regions, only positively charged ions is going to be there. Okay, and here after this depletion, after the XD to the work, we may say it's neutral. There is still a one electron is combined with the ionized donors, with the donors to set the neutral. Okay. But at the depletion region, because of the built-in potential and corresponding electric field, the electron is going to be, has to be moved to the metal so that it can have net charges in there. And actually we can calculate this part like ND over K E naught XD is going to be Emax, and that Emax is corresponding to this part, Emax. Okay? Well, all you have to do is you just integrate the charges is going to be corresponding to the electric field, right? And if you integrate, well, I should say the other way around, but let me make it. Let me write down the Poisson's equations. If you have a second derivative of the potentials, then it's going to be related to the charges. Okay, that is the Poisson's equations, K E naught, something like this. You have a integration of if you make a first derivative of the potential, and that is related to the electric field. Okay, so all you have to do is just make an integration from 0 to XD, so that you have a left-hand side part, and that is going to be related to the electric field. And that's how you can get. And here, phi max also can be calculated. You make a second integral of this, and then that is Q and D K E naught XD square. All right. So from this equation, the important feature of this equation is that from here you can actually calculate the depletion length, which is very important. Okay, which you cannot see with the TEM or SEM whatever, but there is field inside. That's what this depletion region length, and that can be calculated. And all these numbers, we know all these numbers. Okay, phi I can be measured separately, the built-in potential, and all these numbers we know. The doping density, for example, then we know how much, how long the depletion width should be after we make a junctions. And the charges in the semiconductor, the Q there, is going to be Q K E naught N D phi I. Okay? All these things can be calculated. Okay. Now, what happens if we apply the bias to this junctions? Application of a bias. So that means if an application of the any voltages to these junctions, the junction is going to look like this. That's what we have seen, right? But if you apply the voltages to these junctions, the first happens in this junction is that we cannot define fermi energies because it's not in equilibrium. Anymore. Okay, that's what happens inside the materials if we apply the voltages to these junctions. And what is going to happen is that you're going to enhance or decrease. You move up and down this conduction band with the application of the voltages. So if you apply the forward bias, then this conduction band is going to move upwards, okay? And then if you apply the reverse bias, then this conduction band is going to go downwards. And obviously you can see with the forward bias, electrons can flow, more electrons can easily flow to the metals. And if you apply the reverse bias, the electrons cannot go to the metals. And the electron, the direction of the electrons to flow has to be from the semiconductor to the metals, because remember, the work function of metal is greater than the work function of a semiconductor. So the electron flow has been defined from that point, and then if you apply that Schottky junctions, okay, then this application of the voltage is going to work like this, so that if you measure the applied voltages and the current of these junctions, if you have a forward bias, then you have an exponential increase in the current, because this height, the band bending of a conduction band, has exponentially proportional to the number of electrons from the Boltzmann statistics. Remember? Okay. So with the application of voltages, conduction band is going to be distorted in such a way that more electrons can flow to the metals, and then the increase of the electrons number should be proportional, exponentially proportional to the applied voltages. So that's why we have this exponential increase in the currents. But if you apply the reverse bias, then no electrons can flow. Okay? And then if you apply very much reverse bias, then we're going to have sudden increase, very sharp increase, like a cliff, very sharp increase in the current. We call this the breakdown of the junctions. Well, this breakdown has not, it's not going to do any harm to the junctions actually. Breakdown is breakdown. But if you have a lot of huge amount of a current, then you're going to have IR voltage drop, and then that is I square R is going to be joule heating. That is energies. So from this breakdown, you're going to generate a lot of heat, and then that heat is going to melt down actually the junctions. So breakdown itself is not going to do any harm, but the heat which can be generated from this breakdown will going to ruin the junctions. So we have some devices utilizing this breakdown, because at this breakdown you are having the fixed voltages. No matter what the current is passing, right? So that is a voltage regulator. So if you take advantage of this breakdown phenomenon, that is going to be called the genodiode. And you are going to allow the device to let the current flow be below the level which can generate the heat to ruin the device. If you be careful about that, then this phenomenon can be useful to for the devices which you need sometimes you have to have regulators, right? Fixed voltages devices. Anyway, so that's what happens in the diode. So you can see the reverse bias current is almost zero, and forward bias has to be proportional to the current of a forward bias has to be proportional to each VA, something like that. Okay? And XD, the depletion length here, say this is the XD. Beyond this is an equilibrium, the flat. The XD has to be regulated where they apply the voltages. And the way it is changing where they apply voltages is going to be QND phi I minus VA. Okay, all you have to do is just changing here. It used to be phi I without the VA. If you do not apply the voltages to the junctions, then the XD is going to be defined with just a built-in potential, right? If you apply the voltages, then the XD is going to be expressed in this fashion. And here the sign of this applied voltages depends on the forward bias or reverse bias. Obviously, if you apply the forward bias, it should be minus like this. And if you apply the reverse bias, then XD should be extended with the reverse bias. Now, another important parameters in the metal semiconductor junction is the capacitance. And that capacitance is the charge changes with respect to the applied voltages. There's a definition of the capacitance in the low-level injections, of course. We're going to talk about this low-level injections in the detail later, but in a usual case, the capacitance should be defined as something like that, and then you know we have a charges here, and then all you have to do is these charges make a derivative with respect to the VA. That's what you're going to do. So say these charges in this semiconductor part is going to be Ke naught ND phi I minus VA with the application of the voltages. It's going to be like this. So you make a first derivative of this equation with respect to the VA, then you end up with A Q K E naught ND over phi I minus VA scalar. Okay? Now, this looks complicated, but if you arrange this thing, 1 over a reciprocal of C square, then it's going to be phi I minus VA, where gamma is going to be 2 phi I. Oh, wait a minute. You can see what the gamma is going to look like. And then you can arrange this thing. Let me just write down QK E naught ND minus 2 over A QK E naught ND VA. Okay? So from this equation, if you make a plot, one over C squared, okay, with respect to VA, then you're going to have a straight line like this, and the intercept, that is going to be, that is corresponding to gamma phi I, okay? And then slope is related to the minus gamma. So we can obtain the ND from gamma values there, right? So if you want to know the doping level of your semiconductor, all you have to do is make a blocking contact with the metals, and then you measure the capacitance, application of the voltages, VA, and measure the capacitance with respect to the application of the voltages, then you're supposed to have a straight line. And then that straight line contains a phi I that is related to the built-in potential, how much potential exists inside these junctions. And another information you can get is this is the most exact way to find out the doping of your semiconductors. Okay? It's a very useful information you can get, and that's very important. Now, what about the ohmic contact? For ohmic contact, phi m should be less than phi s in n-type. All right? Or if you have a heavy doping, then you're going to have ohmic contact. Let me explain about this heavy doping for tunneling. Now, if you doping heavily, then you're supposed in rectifying contact, you're supposed to have a bending like this, and this depletion width is inversely proportional to the square root of over square root of doping levels, right? So if you dope heavily, then this XD becomes small and small, so that finally you can get a tunneling here. So even though it is a rectifying contact, you can have the tunneling through this mechanisms. And this is very important in a semiconductor devices, because when you make a contact of a semiconductor devices, like in a CMOS structures, we usually have field oxide and field oxide to separate the transistors, and then you're going to have, if you use the P substrate, then you're going to have an N well, and then P plus junctions like this. And then here, the rest of the part, you're going to have N plus and M plus. And that is the CMOS structures, which commonly used for the SRAMs, right? It's for memory devices. Now, when you finish this foundation, you're going to deposit the dielectric layers like SiO2, things like that, and make a contact. We call that contact. And we call this interlayer dielectrics, interlayer dielectrics. Okay, and then make a contact hole, and then you should deposit the metals and make a pattern so that you form metals like this. Okay, and you are going to have a metal-semiconductor junctions at this part. Right? You are going to have metal-semiconductor junctions here, and here, and here, and here at the same time. Okay, M plus and metals, there's no problem because there's ohmic contact all the time. But in a P plus and metals, is a rectifying contact. So to overcome this, you have to dope this P plus very heavily so that the tunneling is going to happen through this to make an ohmic contact. If you cannot make ohmic contact, then the resistance is so high so that the inlet or outlet signals can be delivered to this device. So you want to make this contact resistance as small as possible. And how can you make it? We use this tunneling phenomenon. Okay? Otherwise, we're going to have a very big resistance, so that we cannot make a ohmic contact. Now, finally, let me just show you the device which is taking advantage of this depletion regions, and that is metal-semiconductor field effect transistors, and that is going to be called the MOSFET. Metal-semiconductor field effect transistor, MOSFET. Okay? And how do you make it? In the silicon wafer. Okay, this is the silicon wafer. You start out with the heavily almost intrinsic high resistance silicon wafer, p-type. Okay, and then you doping or whatever, you make a M- layers on top of it, and then you're going to make a gate source drain, and that should be N plus. Okay, and then this is just metal. The important thing here is no gate oxide. That is a difference from all normal MOS transistors. If you just make a metal, deposit a metal on top of the silicon, then according to the bias to the metal, it's going to create the XD is going to be modulated according to the equations that we have, so that the depletion is going to form something like this. And depending on the VA, we can change the length of the XD so that we can modulate the resistance between source and drain. Okay, so the current between source and drain is going to be modulated to the application of the voltages. Okay? That's how this MOSFET transistor is going to work. That is the working principle. We are going to talk about the details of this after the almost the end of this class. Okay, we are going to discuss about the MOS transistors, bipolar transistors, and other transistors as well in this class later, very end of this class. Okay, next class is going to be on Wednesday, and we're going to talk about the PN junctions, which is more important than this metal semiconductor junctions. Right? Any questions? Well, if you have questions, please drop by my office by any. It's on the third floor of this building. Okay? Okay, I'll see you next Wednesday then.